All right, now let's look, now having had potential, and we'll certainly come back to that where we actually calculate the potential due to collections of charges. But let's look now at potential difference. This is very closely related to potential. The electric potential difference between 2 points is the energy per unit charge gained as the charge moves from point A to point B. So it's the energy per charge gained as the charge moves from point A to point B. So it is also, we can think of it as the difference between the potentials VB minus VA. But that's the same statement. That is the energy per unit charge gained, which is the same as the difference in the potential, since potential, remember, is the energy per charge. Okay, so this is equal then to the change in potential energy for the charge over Q. Now the units for this are joules per coulomb, because we have energy over charge, but we make this to be a volt. So this is equal to 1 volt. That's after the physicist Voltaire, and so when I abbreviate it, it's a capital V. Now, since our change in potential energy is negative QE times delta X, in fact, this is going to be E in the X direction. So we're assuming that the electric field is in the same direction as the displacement, as it has been so far. We're defining delta V as delta PE over Q. I've already showed that that is equal to negative of EX delta X. So I can define my electric field in terms of delta V. So it's going to be negative delta V over delta X. Right, so this is an expression for the electric field that is based on the voltage, or the potential, or the potential difference rather. And it also gives us a more typical unit for the electric field. Remember, I mentioned this previously, but a Newton per Coulomb is common for the electric field, but more common is the volt per meter for the electric field. So from here on out, I'll try to use volts per meter, though I'll sort of go back and forth. All right, let's move on. There are a couple little things. I'm going to skip this. I think I can show you this without saying it in words. We have a couple of things, is that positive charges tend to accelerate from high to low potential. So if I have a positive charge, it's going to go from a high to a low potential. So for example here, I have a charge. Remember I said I have 2 plates, a positive plate, and this is going to be high potential. The positive plate charges, positive charges there have lots of energy per unit charge. And over here, this is going to be low potential. And positive charges are going to tend to move from high to low. So if I have a positive charge, it's going to move in this direction. Contrast that, if I have a negative charge, they tend to move from low to high potential. So if I have a negative charge here, it's going to tend to move in that direction, as you would expect from the electric field. Negative charges will always flow opposite the direction of the electric field lines. Remember, the electric field lines are the direction that a positive test particle would travel if it was in that situation. So a negative test particle is going to move the opposite direction. All right. Now this has some scenarios. So let's say that I have a plot of V versus position. I'll just say it's X. Now let's say the plot looks like this, for example. And let's say that I put a positive test charge right here at this position, say X equal A. I put a positive test charge there at X equal A. Since positive test charges tend to accelerate from high to low potential, that positive test charge is going to move in that direction because it wants to find a lower potential. That would be like following the electric field lines. Now, however, if this was a negative test charge, say I had a negative test charge right here, negative test charges tend to go from low to high potential, and so it's going to move in that direction. A negative test charge will move in that direction. All right. Now let's say, for example, what if I had a charge here? Right. Now, if this was a positive charge, they tend to go from high to low potential. A positive charge would be stationary. It would not move. We call it a stable equilibrium. So it's not moving. It's not going to move in any way. However, a negative charge, if I put a negative charge, see, I'm switching up my colors a little bit here. But if I put a negative charge right here, negative charges tend to go from low to high potential. A negative charge could go in either direction. depending upon how the potential is set up. You'll see some more questions like this, sort of qualitatively asking you, what is the direction that a charge would go in this scenario where you have this electric field or this potential well, we call it a potential well. And you'll see a question actually on the next page, and you'll see it in the concept test as well. So you'll get more practice. There's the concept test. I'll leave you to do that. The reason this is important is because you can, by setting up potential distributions, which is fairly simple to do, you can direct the path of a charge. And if you can make a charge do what you want it to do, that's a pretty useful thing. We'll see that when we get into circuits, that making charges do what you want to do. Making charges do what you want them to do can be very useful. All right. If you're in the lab, and most or all of you are, you'll use these simulations. These are really nice for playing around with charges and fields, and there are even some games with this field hockey. So you can go and play with these. So if you're in lab, you've already played with them. You can also just Google PHET and, I don't know, do charges and fields or electric hockey or something like that. Just Google those terms, and it'll come up. It'll be one of the first things. We will pause there and pick back up with this.